Let's turn to probability. In this outcome, we'll work along the probability scale from 0 to 1, meet mutually exclusive and complementary events, compare experimental and theoretical models, use expectation to predict results, and finish with conditional probability and tree diagrams. Here's what's ahead. We'll read the probability scale from 0 to 1, handle mutually exclusive events with the addition rule, and use the complement rule that the probability of not A is 1 minus the probability of A. Then we'll contrast experimental and theoretical probability, use expectation, E equals NP, to predict outcomes, and work through conditional probability with tree diagrams. Every probability is a number somewhere between 0 and 1, inclusive. 0 means the event is impossible, 1 means it's certain, and a half sits right in the middle for an even chance. You can write a probability as a fraction, a decimal, or a percentage, so 0.25, a quarter, and 25% are all the same thing. And a key idea, the probabilities of all the possible outcomes always add up to 1. A little vocabulary first. An experiment is any repeatable process with an uncertain result, like rolling a die. An outcome is a single possible result, such as rolling a 4. An event is a set of one or more outcomes we're interested in, say, rolling an even number. The sample space is the complete list of all possible outcomes, and the probability of A is just the chance that event A happens. Theoretical probability is what we use when every outcome is equally likely. You work it out from the setup itself. The probability of A is the number of favorable outcomes divided by the total number of outcomes. So for a die, the probability of an even number is 3 divided by 6, which is a half. No experiment is needed at all, and you should always simplify the fraction where you can. Let's try 1. We roll a fair 6-sided die once and want the probability of scoring more than 4. The favorable outcomes are 5 and 6, so that's 2 of them, out of 6 possible scores. That gives 2 divided by 6, which simplifies to 1/3, or about 0.333. So the probability of scoring more than 4 is 1/3. Two events are called mutually exclusive when they simply can't both happen at once, like rolling a 2 and rolling a 5 on a single throw. They share no outcomes at all. When events are mutually exclusive, the probability of A or B is just the probability of A plus the probability of B. That's the addition rule, and it extends happily to 3 or more events. You just keep adding the individual probabilities. Here's the addition rule at work. A bag holds 5 red, 3 blue, and 2 green counters, 10 in total, and we draw 1 at random. The probability of blue is 3/10, or 0.3, and the probability of green is 2/10, 0.2. Since a counter can't be both blue and green, these are mutually exclusive, so we simply add them. That gives 0.3 plus 0.2, which is 0.5. The complement of an event A is simply A not happening, and we write it A dash, or not A. Between them, A and not A cover every possibility, so their probabilities must add to 1. Rearranging that gives a really useful rule. The probability of not A equals 1 minus the probability of A. It's especially handy when the thing not happening is easier to count. For instance, the probability of at least 1 is 1 minus the probability of none. Let's use it. Suppose the probability that it rains on a given day is 0.35, and we want the probability that it doesn't rain. Not raining is the complement of raining, so we take 1 minus the probability of rain. That's 1 minus 0.35, which comes to 0.65. so there's a 65% chance of a dry day. Quick check. If a die is rolled, a roll a 3 and roll an odd number, mutually exclusive. And can you explain why? If the probability of A is 0.42, what's the probability of not A? And if a spinner gives a probability of winning of 1/5, what's the probability of losing? Have a think. It's worth pinning down the difference between the two kinds of probability. Theoretical probability is worked out from the setup, assuming outcomes are equally likely, so it's a fixed value with no trials needed, like the probability of a head being 0.5. Experimental probability, on the other hand, is measured by actually running trials. It's the relative frequency, successes over trials, and it varies from sample to sample, such as 47 heads in 100 giving 0.47. Let's dig into experimental probability. You find it by performing the experiment many times over, and the relative frequency is the number of successes divided by the number of trials. This gives an estimate of the true probability, and the more trials you run, the closer it tends to settle towards the theoretical value, an idea known as the law of large numbers. It's particularly useful when outcomes aren't equally likely, like a biased die. Here's an example with real data. A drawing pin is dropped 200 times and lands point up on 130 of them. The relative frequency is successes over trials, so 130 divided by 200, which is 0.65. Bear in mind, this is an experimental estimate rather than an exact value, but our best guess is that the pin lands point up with probability about 0.65. Expectation is all about predicting how often something should occur. The expected number is n times p, written E equals NP, where n is the number of trials and p is the probability of the event. It's important to treat this as a prediction, not a cast-iron guarantee. Real results will scatter around the expected value. Comparing E equals NP with actual data is a great way to test whether a model fits. Let's predict with it. A fair coin is tossed 80 times, so P is 0.5 and N is 80. The expected number of heads is N times P. That's 80 times 0.5, which is 40. Now, if we actually observed 47 heads, that's close enough to 40 that the coin looks perfectly fair. Small differences like this are just the natural result of chance. Now, a case where the numbers raise an eyebrow. A die is rolled 120 times. For a fair die, the probability of a 6 is 1/6, so the expected number of sixes is n times p, 120 times 1/6, which is 20. But suppose we actually see 34 sixes. That's a good deal higher than 20, enough to make us suspect the die might be biased towards 6. Let's gather some terms. Mutually exclusive events are ones that can't both happen at the same time. The complement, a dash, is the event that A doesn't happen, with probability 1 minus the probability of A. Relative frequency is that experimental estimate, successes over trials. Expectation, E equals NP, is the predicted number of successes in n trials. And conditional probability, the probability of B given A, is the chance of B once A has already happened. Conditional probability is the probability of one event given that another has already taken place. We write it as the probability of B given A. The key idea is that knowing A has happened changes the sample space, the set of possibilities you're now working within. This comes up constantly in without replacement problems. Once you've removed an item, the totals shift for the next draw. And to combine events, you multiply along the branches. The probability of A and B is the probability of A times the probability of B given A. Let's see it. A box has 4 red and 6 blue pens, 10 in all, and we draw 2 without replacing the first. On the first draw, the probability of red is 4/10, or 0.4. Now 1 red's gone, leaving 3 reds among 9 pens, so the probability of a second red, given the first was red, is 3/9, a third. Multiplying along the branches, 4/10 times 3/9 gives 12/90, which simplifies to 2/15, about 0.133. Tree diagrams are a lovely way to lay out problems that happen in stages. Each branch is labeled with its probability, and the branches coming out of any one point always add up to 1. To find the chance of a combined outcome, an AND, you multiply along the branches. For an OR, where separate roots lead to the same result, you add those roots together. They're especially helpful for conditional without replacement problems. Back to our 4 red and 6 blue pens, drawn 2 without replacement, and this time we want 1 of each color. Red then blue is 4/10 times 6/9, which is 24/90. Blue then red is 6/10 times 4/9, also 24/90. Those 2 roots are mutually exclusive, so we add them, giving 48/90, which simplifies to 8/15, about 0.533. Let's crystallize the 2 rules. AND means both events must happen, and you travel along the branches multiplying. So the probability of A and B is the probability of A times the probability of B given A, like red, then red, giving 2/15. OR means either event may happen, and for exclusive events, you add the separate branches, so the probability of A or B is the probability of A plus the probability of B, like our red-blue and blue-red roots adding to 8/15. A few pitfalls to steer around. Never let a probability stray above 1 or below 0. Those are impossible. Don't add probabilities unless the events really are mutually exclusive. Remember the totals change in a without replacement problem. Don't muddle the probability of B given A with the probability of A and B. Treat expectation as a prediction, not a promise, and always simplify fractions and round sensibly. Time to check yourself. A coin is tossed 300 times, so using E equals NP, how many tails would you expect? A bag has 3 white and 7 black balls, and 2 are drawn without replacement. What's the probability both are black? Can you explain in your own words the difference between theoretical and experimental probability? And why does the sample space shrink in a without replacement problem? Let's pull the outcome together. Probabilities run from 0 to 1, and all the outcomes sum to 1. For mutually exclusive events, the probability of A or B is the probability of A plus the probability of B. The complement rule says the probability of not A is 1 minus the probability of A. Experimental probability is successes over trials, which we compare against theory. Expectation, E equals NP, predicts results and tests models. And conditional probability means multiplying along the branches of a tree.